All right, hello everybody. In our last video, what we talked about was the moment about a point. And we talked about this idea of a force times the distance around a point. In this video, we're going to talk about the concept of moment about some kind of line. And a lot of the same principles are there, so I started with a little review here. When we talked about moment about a point, we said it's a force times a perpendicular distance. And what really became interesting is when we moved into the 3D realm and we said we had R cross F. We could do a cross product between two vectors, which would give us a moment about a point. So let's go ahead and move on to today's concept of moment about a line. All right, so in order to talk about this moment about a line, what we're going to use to find this moment is a scalar product, also known as a dot product. So I think you probably learned this somewhere along the lines, but to refresh your memory, let's define a scalar product, also known, of course, as a dot product. So if I have two vectors, vector P, and I want to have a dot product with vector Q, the way I do this is I have the quantity, or the magnitude of P times the magnitude of Q times the cosine of the angle in between. And the reason it's called a scalar product is because I end up with a scalar, not a vector. So I start off with two vectors, and so this gives me just magnitude only. So the next little thing that we need to define is the triple product for three vectors. So the triple product of three vectors is a scalar product of a line with a vector product of a radial arm and a force. What? I know that sounded crazy, but let me write it out and I think it'll make more sense. There, now it's not clear at all, is it? Well, this is the easiest way that you could probably represent this. So the moment, which notice I don't have it as a vector, it is a scalar, is equal to this line, which is a vector. And it's going to be a dot product of R cross F, which we learned last time for our R cross F being the moment about a point. So the extra little bit here is that little L, and what that allows us to do is find the moment around a line with a radial distance R. And what this would actually look like is the moment about this line is equal to, and we're going to have our little matrix. See, now instead of our I, J, and K hats up top, what I have is LX, LY, and LZ, or basically it's the line's magnitude in the X, Y, and Z direction. RX, RY, RZ. And the order is important. You have to do line first, then radial arm, then the force to get your signs right. FX, FY, and FZ. So that's what our matrix ends up looking like. Of course, you could expand it and it would look, I'm sure you can do this, but it would look like this. Something like that. So I think you can best see this with an example. So I brought an example. Bring it up here. In this example, what we have is this triangular shape, and what we're given is, you can see it's held by two cables. So in essence, it can rotate about this, those 2 points B and D. It can pivot around those. So I could draw, for instance, a line that connects B and D. That's kind of like the pivot point. And then there's C and F and A and E that are holding in place. In this case, what we're given is that the tension of CF is equal to 33 newtons, and we want to find the moment of that about the line BD, that green line. So the first step in these problems is to say, well, I need to draw it out with my vector, which I see 33 newtons. I need to find my line, which I see as BD, and then I also need some kind of radial arm. So for my radial arm, I need to go from the line out to this force. Now this could actually be anywhere along here. I could go from B up to C or whatever, but when I try and think what's the easiest way, I'm trying to only do in one direction in my I, J, or K, or something like that, right? Or the minimal amount of stuff that I can have, whatever is the easiest way to represent it. So with that in mind, let's start with that radial arm. That radial arm, the way I have it drawn in the x direction, I stay in that YZ plane, so x is 0 plus. Now this is kind of hard. You got to look at it a little bit to figure out how far I am in the y direction. How high do I go? I can see D is what, 0.7 from the ground, and C is 0.9. So that leaves me with 0.2, right? 0.9 minus 0.7 J hat, and then in the Z direction, I go that negative 0.4 K hat. So that's my R, my radial arm in component form. Next thing I'm going to do is I'm going to put this force CF into vector form. We said how to do that is first you're going to find the length of CF, which gives me something like 1.1 meters. Then I can put it into component form, so the tension in CF, it looks awful, in CF is equal to, and if I multiply that through, I end up with something like 18 newtons in the I hat, minus 27 newtons in the J hat, minus 6 newtons in the K hat. So now I have a radial arm, and I have my tension. The last thing I need to do is this line from B to D. I'm going to treat it just like I did with that vector. So the first step to put it into a X, Y, and Z component or proportionality form would be to find the length of line DB. And I got a total length of 1.25 meters. So looking at vector DB, then I can put it into component form, and multiplying it through, I end up with 0.96 I hat minus 0.28 J hat plus 0 K hat. So once I have these three pieces of information in component form, I look back and say, well, what I just defined is the moment about a line. In this case, the line is this moment about dB is equal to the magnitude, or the vector dB cross product with R cross, dot product with R cross T, C, F. So putting that into my matrix form, what I have with, and a top line is going to be the components of this line, since that's first in the order. So I have 0.96 minus 0.28 and 0. The second one being the radial, so that was the very first thing I did, that 0 and that 0.2 and the minus 0.4, so I have 0, 0.2 and minus 0.4, and the last one being that tension, that tensile force. Magnitude is 18, minus 27, negative 6. And if I expand all that thing, that whole business out up with a negative 11.52 plus 2.016 plus 0. Once again, you're not going to have any I hat, J hat, K hat. This is actually just a scalar. It's just a number. It's a magnitude about that line. And I end up with 9.50 Newton meters. So that's kind of how these problems are done. I will say that in the textbook, what they'll do sometimes is they'll want to find the moment about an axis. Like say you had the exact same thing, only instead you wanted to find the moment about the x-axis down here. If you wanted to do that, the process is the same, except when you get to this line up top, if you wanted to do it about the x-axis, you just put a 1. It's like 100% in the x-axis. It's an infinite in length divided by the distance, right? So to have 1, 0, 0. If I wanted the moment about the y-axis, it would be 0, 1, 0, and of course the z-axis would be 0, 0, 1 for that top line. So that's something else that they'll do. I'm a bigger fan of using the Jedi mind trick. If they're going to do it about the axis, you should be able to do that. But when you have something complicated like trying to find it about this line where you literally just cannot quite envision what that would, Jedi mind trick, you can use it, but it becomes really complicated. Real Jedi master to be able to do that. So hope that was helpful, and I will talk to you all later. Thanks.